In last we studied about the Gauss law. It is given by surface integral of E dot ds is equal to 1 upon epsilon naught summation over I is equal to 1 to n qi. This is a Gauss law. Now second, we consider second case where the charge is outside the surface. Here we consider q is the charge which is outside this body. If the charge is outside the surface as shown in figure, the surface can be divided into so many parts: surface S1, S2, S3 and S4, S1, S2, S3 and S4. Area substituting the same solid angle Q. This is solid angle which is same. But at S1 and S3, direction of normals are opposite to that of S2 and S4. Therefore, contribution of the two pairs of surface integral are equal and opposite. Consequently, the integral vanishes, that is, surface integral of E dot ds, surface integral of E dot n into ds, which is equal to 0. Now, this is Gauss law in other form, that is called as divergence form. Now this is surface integral of E dot n into ds is equal to 1 upon epsilon naught V volume integral of rho. Rho is the surface charge density into dV, because Q charge is equal to volume integral of rho into dV. This is the integral form of Gauss law. Changing surface integral into volume integral, then you know about the Gauss divergence theorem. Volume integral of divergence E dot dV is equal to 1 upon epsilon naught V rho into dV. So this equation shows that divergence of E is equal to rho upon epsilon naught, which is the differential form of Gauss law. Now, application of the Gauss law. Now consider first case, field due to spherical symmetric charge distribution. Now at an external point, this is the figure. Let a charge Q be distributed uniformly over a sphere of radius r. This is radius r and Q is distributed uniformly with sphere of radius r with center at O. Let A be the external point at a distance r. Here is the A external point. This distance from the center O is small r, where the electric field intensity is required. In order to calculate the electric field intensity at point A, we draw another concentric sphere shown by this dotted line, known as Gaussian spherical surface with radius r. As a distribution of charge is uniform, the electric field strength E at every point of this sphere is the same and is directed along the outward drawn normal because of Gauss law. For a small surface, it is clearly seen that angle between E and ds is 0, because ds and E is along same direction. Therefore, E dot ds is equal to E dot ds cos 0. Cos 0 value is 1. Therefore, it is E dot ds. So, now electric flux through entire Gaussian surface is given by phi is equal to closed integral of E dot ds. Substitute value of integration of ds, that is 4 pi r square. We get according to Gauss law, E dot 4 pi r square is equal to q upon epsilon naught, or electric field at that point is given by 1 upon 4 pi epsilon naught q upon r square. Thus the electric field intensity due to a uniformly charged sphere at any external point is the same as if the entire charge on it were concentrated at center of the sphere. If the point A lies on the surface of the sphere, then R is equal to capital R, and hence the field intensity is given by this formula: E is equal to 1 upon 4 pi epsilon naught dot Q upon capital R square. Now consider another case where the point is inside the sphere at internal point. Let us consider the point A inside the sphere at distance r. This is the A which is inside the sphere, and this distance from the center is small r. Consider Gaussian surface at point A as shown by the dotted line. This is Gaussian surface. Phi E is given by E into 4 pi r square. Let q dash be the part of the total charge q which is lying within the Gaussian surface radius r. The Gauss law gives electric flux phi E is equal to q dash upon epsilon naught. Therefore, E into 4 pi r square is equal to q dash upon epsilon naught. As the sphere is uniformly charged, the charge density, that is the charge per unit volume rho, is constant throughout the sphere, and its value is given by electric field E is equal to 1 upon 4 pi epsilon naught q dot small r upon capital R cube. This expression shows that the electric field intensity due to a uniformly charged sphere at internal point is proportional to distance r of the point from the center. If the sphere is conducting, that is metallic, then there will be no charges within the Gaussian surface and electric flux is 0. That is, electric field intensity is equal to 0. This is due to the fact that entire charge will reside on the outer surface.